Hello everyone. So in the previous session we have solved the problems on Cauchy's integral theorem and Cauchy's theorem. So let me continue the theorem with the same lesson. So here is a theorem, consequence of Cauchy's integral theorem. One more name is Morera's theorem. Fine, so one and the same, and one more name is converse of Cauchy's theorem. So in Cauchy's theorem what we have learnt, for any closed curve C, integral over C f of z into dz is equal to 0. This is what the Cauchy's integral theorem is. If f of z is analytical function, then as per the Cauchy's theorem we can write integral over f of z dz is equal to 0. Now it is just a converse of Cauchy's theorem, that is reverse. So if f of z is continuous in open set G in the complex plane C, and integral over C f of t into dt is equal to 0 for every simple closed curve C in G, then f of z is analytic in G. In the sense, if this condition is true, we have to prove f of z is analytical. Whereas in the previous theorem, that is Cauchy's theorem, what we have proved is if f of z is analytical, then this condition satisfies. So it is something like reverse of a Cauchy's theorem. So that is why we say converse of Cauchy's theorem. So one and the same. When they ask in the exam, when they asked you to prove Morera's theorem or Cauchy's converse of Cauchy's theorem or consequence of Cauchy's integral theorem, so you have to write the same. So you have to write the statement, whatever the theorems you have in complex analysis, so you have to remember the statements for the standard theorems. Now let me come into the proof. So let me prove here. So let us consider a complex plane C, and let us consider 2 points, say z1 and z2. So whatever I am telling manually, you have to write all those statements. Let z1 and z2 be any 2 points in G. Anyhow, I will send you the notes, but I am just explaining manually. So let z1 and z2 are any 2 points in a complex plane, and let c1 and c2 be any 2 curves which joins those points. So c1 and c2 are 2 curves which join the point z1 to z2. So there exists a path from z1 to z2. Fine. Now we can say that C1 to C2 is a simple closed curve, right? Now let me consider an integral. Let us consider an integral f of z into dz is equal to 0. This is by Cauchy's theorem, right? So if this is true, we have to prove that f of z is analytical. This is the converse part of a Cauchy's theorem, and we say this as Morera's theorem as well. And it is asked in the year 2017. So you have to practice this well. Now I have assumed the integral value. Instead of variability, I have considered it as z. Now from the diagram it is clear that, so I can split the curve into 2 parts, right? So overall curve C can be splitted into 2 parts, that is C1 and C2. So integral can be written as first integral along C1 f of z into dz, and second integral along C2, so f of z into, and you can note that C2 is in opposite direction to C1. You can look at the direction of arrow. So Z1 to C1, Z2 is, C1 is in this direction, whereas in C2 is opposite direction. So that is why I have to put minus sign here. Fine. Now as per the properties of integral, I can shift an integral sign, negative sign here, so that I'll get C2 f of z into dz, which is equal to 0. Meaning is that integral over C1 f of z into dz will be is equal to C2 into f of z into dz. That is, it is path independent. Anyhow, it is one of the consequence of Cauchy's integral theorem. So I can write this as, therefore from the points, moving a point from z1 to z2 is path independent. So this is what the corollary of Cauchy's theorem, we have already proved it. So is path independent. So if that was the case, meaning is f of z is a function which is independent of z1 and z2. So if that was the case, let me take any arbitrary point z. So I'm going to consider any arbitrary point z in this plane, total plane G. So let me consider this total plane as G, and in such a way that let z plus h be any neighborhood of G, z. In the sense, suppose I'm going to consider a point z, and z plus h be neighborhood, in the sense it is at a distance of h. So what z plus h is at a distance of h from z. Fine. So z plus h is neighborhood of a point z, and let me take t as a variable. Why? Because we have a t in the theorem. So t as a variable. Fine. I'm repeating once again. Let z be any arbitrary point in the point G, and z plus h be any neighborhood of, I'll write here, any neighborhood of G. and let me take a variable t. Why? Because we have in the theorem statement it is t. Now let us consider an integral f of z is equal to a to z f of t into dt. Why? Because it is path independent, so we can take any of the integral that we wish. F of t into dt, since I have taken t as a variable. Fine. So let me take this as equation 1. This is with reference to point z. Since I have chosen one more point in its neighborhood of z, so it is z plus h. Therefore I can write the z plus h as, z will change this to z plus h. So a to z plus h f of t into dt. Let me take this as equation 2. Now let me subtract both the equation. 1 minus 2 will give us, let me subtract LHS part, so that you will get f of z minus f of z plus h will be is equal to integral over a to z f of t into dt minus integral over a to z plus h f of t into dt. I have just subtracted equation 1 and 2, so LHS part I have written here, RHS part I have written here. Hope so it is clear. Now what I am going to do is, let me divide both sides with h. Divide h on both sides. Fine. So let me divide. I'll just continue here. So when you divide it with h on both sides, so what will become? F of z minus f of z plus h divided by h is equal to, I am dividing both sides by h. So instead of writing whole divided by h, I can write 1 divided by h integral over a to z f of t into dt minus integral over a to z plus h f of t into dt. One and the same. I have divided it both sides by 1 by h. Clear? Now let me arrange the given term. So whatever I have written here, first let me write this term. So I'll just rewrite the term in order to apply the property. So I have minus here. Let me take minus common factor so that I can write this as a to z plus h. So it will become f of t dt minus, since I have taken minus as a common factor. See here, if you are going to multiply minus inside, you will get back the previous step. See here, minus into a to z plus h, you will get this term. Next, minus into minus plus, you will get this term. In the RHS also, I will take minus common term. So instead of doing all these things, you can take minus directly. Instead of subtracting 1 minus 2, you can do 2 minus 1. You will get back the same result. So it doesn't matter. However, let me do this. So minus and minus get cancelled. You will get f of z plus h minus f of z divided by h is equal to 1 by h into. Now what I'm going to do is, since I have integral a to z plus h f of t into dt here minus integral over a to z f of t into dt. Right? Now what I'm going to do is, as per the properties of integral, when you're going to interchange upper and lower limit, you will get a minus sign. Right? Properties of integral says that when the lower and upper limit of the integrals is interchanged, then the integral changes by sign. So it is the basic property and it is there in second PUC. Properties of integral, if you want, you can search. So a plus h f of t into dt. Now I'm going to exchange the integral so that I can write plus, since I have lower limit a, I'll write it z to a f of t into dt. I have interchanged the integral, lower limit and upper limit, so that is why minus will become plus. Hope so this step is clear. Now again applying the property of integral, see here, since here the lower limit is a, here the upper limit is a. Further, if you are finding difficulty, let me write one more step. So 1 by z. What I'm going to do is, first let me write this one. This term I'm going to write first. See here, I'll just write this here, z to a f of t dt plus integral, I'll write this here, a to z plus h f of t into dt. Fine. Now here whatever the limits you have is both same. Right? So if that was the case, as per the property of integral, I can combine this. Moreover, integrand should be same. Since in this case both the integrand is same, so I can combine this as in 1 by h into integral from z to z plus h f of t into dt. Further, if you split this by using a, you will get back the previous step only. It is from the properties of integral. Let me write RHS as it is. LHS as it is. Fine. This is what I have. Now what I am going to do is, let me subtract minus f of z on both sides. Minus f of z on both side. So when you do that, what I'm going to write is, in the previous step, f of z plus h minus f of z divided by h, I'm going to subtract with minus f of z. Fine. Similarly, which is equal to 1 by h into integral over z to z plus h f of t into dt minus f of z I have. Clear? Now let me simplify further. So how can we write this as? See here, I'll just manipulate the terms here. I can write this as z to z plus h f of t into dt. Now I am just multiply and divide with h. See here. So again, when you're going to simplify, you'll get back the previous step. See, h and h get cancelled. So I can write this as h by h into f of z. Fine. Again, I'll just write this as 1 by z into integral over z to z plus h f of t into dt. Now I'll just separate this term so that I can write this as f of z divided by h. Now how can I write h as? We can write h as integral over z to z plus h into dt. I'm repeating this step once again. Why? Because it is a bit confusing. See here, what I did is, first I have separated f of z by h. I have written this term separately. Now h can be written as integral over z to z plus h dt. Why? Because if you simplify this, you will get back h only. If you want, I'll show you here. See here, I'll just write here. See, integral over h to z to z plus h dt. So integration of dt is t. Upper limit is z plus h. Now let me apply the limit. Upper limit is z plus h minus lower limit is z. So plus z minus z cancel. You will get plus h only. Right? So I have written h as integral over z plus h to z into dt. Why? Because I have to combine both the integrals. So that is the reason I have done this. Fine. Now how can I write this as 1 by h into integral over z to z plus h. Now I can combine these two integral, right? Why? Because it is both with respect to t. So I can write this as f of t minus, I have taken 1 by h common. In both the terms, I have taken 1 by h common. I am combining these two integrals so that I can write f of z into dt. I am repeating this step once again. This is one term and this is one term. Both the term 1 by h is common. Next, what I'm going to do is I'm going to combine these two integrals. So I have to take dt as a common factor. So this is what I have. Now let me take this as equation 3 and let me rewrite LHS as it is. That is f of z plus h minus f of z divided by h minus f of z. Fine. Now in the theorem it is given that, see here statement, if f of z is continuous. So f of z is continuous, it is given. Since z is an arbitrary point, so I can extend it. I can write f of t is continuous. Why? Because it is given in the theorem only. So if f of t is continuous in a complex plane z, then I can write, for as per the definition of continuous data, that is epsilon greater than 0, we can write magnitude of f of t minus f of z will be less than epsilon whenever t minus z is less than delta. This is from the definition of continuous function. So since f of t is continuous at z, so I can write f of t minus f of z should be less than epsilon whenever t minus z is less than delta. Fine. This is from the definition of continuous function. Now let me apply modulus for the equation 3. So taking modulus on both sides of equation 3. So when you take modulus on both sides, what I can write, f of z plus h minus f of z divided by h minus f of z. Just I am taking modulus. So 1 by h, I am taking modulus for entire integral z to z plus h, f of t minus f of z into dt. Fine. I am taking modulus of equation 3. Fine. So let me simplify. As you already know that when you are going to split the modulus, something like suppose if you have, as per the property of modulo, suppose if you have modulus of AB, if you want to split this, you have to write less than or equal to modulus of A into modulus of B. So this is what the property of modulus is. Now I am going to apply the same property here. So let me simplify. I am going to simplify here. Theorem looks a bit lengthy, but it is very easy concept. and simple if you practice well. Now how can I write this step as? See here, I am going to write LHS term as it is, f of z plus h minus f of z divided by h minus f of z. Now I am going to split the modulus, thereby what can I write? Less than or equal to 1 by, I am going to split it for each and every term, so that is why I have written less than or equal to. Now let me write the integral z to z plus h f of t minus f of z into modulus of dt. I have splitted it into 3 terms. Fine. Now again, which is less than or equal to 1 by h. Now as per the definition of continuous function, modulus of f of t minus f of z is less than epsilon. So I have already written less than here, so I can replace this with epsilon. Since epsilon is constant, I have taken outside. Now let me write the integral z to z plus h modulus of dt. This is what I have. Now 1 by modulus of h into epsilon. Now what is the value of modulus of dt? So as I already told you, when you are going to simplify this, you will get h, right? See here, I have simplified here. H to h plus h, integration of h to h plus h dt will be t. So if you apply limits, you will get h only. So here also you have the same term. See here, but instead I have modulus. So instead of h, I am going to put it as modulus of h. Fine. One and the same. So h and h get cancelled. So let me write LHS here, f of z plus h minus f of z divided by h minus f of z will be less than epsilon. Now what I'm going to take is, why I'm doing all this thing is, first you have to know that. So here what we have to prove is f of z is analytical. So when do we say a function f of z is analytical? If it is differentiable at all the points, right? So if it is differentiable at all the point, meaning is that, suppose if you are going to find f dash of z, that should be equal to the given function f of z. I am repeating once again, any function f is analytical only when it is differentiable at all the points. So a function f of z is analytical is equivalent of proving f dash of z is equal to f of z. Fine. So that is why I am doing this. F dash of z, the definition I have to arrive. So that is why I am doing all these manipulations. Now as per the definition of differentiability, I have to take the limit, right? So let me take limit n tending to infinity. Limit h tending to 0. Why? Because what is the definition of derivative says, like x plus delta x, f of x plus delta x minus f of x divided by delta x will be limit delta x tending to 0, f of x plus delta x minus f of x by delta x is nothing but derivative d by dx, right? So as per the same concept, I am applying in here. A small change is h, so I am taking limit h tending to 0 here. So when you take limit h tending to 0, f of z plus h minus f of z divided by h, since it is independent of h and moreover it is very small quantity, we can neglect it, and I am going to shift this other side, so you will get f of z. Fine. So when you are going to take limit h tending to 0, it doesn't change. Why? Because it is independent of h, so you can write it as it is. Fine. Now this is the definition of derivative of a function f dash of z. So what I have proved is f dash of z is equal to f of z. It implies that f of z is f dash of z, in the sense I can write f of z derivative exists at every point of g. Therefore I can say f of z is analytical. Fine. Just let me repeat once again. As per the consequence of Cauchy's integral, that is converse of Cauchy's theorem, we have to prove reverse. If this is true, we have to prove f of z is analytical. Whereas Cauchy's theorem is reverse. If f of z is analytical, we can prove, we have this statement, but it is reverse. So that is why we say converse of Cauchy's theorem. What I have assumed is f of z into dz I have assumed, and I have showed that it is independent of path. Now I have assumed the integrand value whatever the given in the problem, and let me take any point z and its neighborhood point z plus h. I have applied the concept and I have taken the difference of these two equations. So when you take difference of the equation and arrange the terms as per the requirement and apply the property, so thereby apply the what we say definition of continuous function. It says that f of t minus f of z is less than epsilon whenever t minus mod z is less than epsilon. So apply the same concept, and what I have proved is f dash of z is equal to f of z. It implies that a function f is differentiable at all the points of z and its neighborhood. That is what the meaning of analytical function is. Therefore f of z is analytical, hence the proof. Hope so it is clear. So notes will be forwarded in the group. Please copy the same. And now let me explain one more theorem. So here is the theorem. We can also say this as Cauchy's inequality. And the statement says that suppose f of z is analytical on the circle. So as you already know, this is the equation of circle in complex form, and f of z less than or equal to m. Then we have to prove that magnitude of fn of a is less than or equal to n factorial by r power of n into m. So you have to remember this statement. Further we are using the same to prove next theorem, that is Leibniz theorem. First let me explain this. To prove this statement, we have to consider a generalized Cauchy's integral formula, or we can say a Cauchy's integral formula for derivative. So remember, Cauchy's integral formula for derivative is same as generalized, let me write here, generalized Cauchy's integral formula, one and the same. So what it says, as per the theorem, fn of a will be equal to n factor. I have already used this formula while solving the problems, so I have told you n number of times. F of z divided by z minus a power of n plus 1 into dz. So this is what the Cauchy's integral integral formula for derivative or generalized Cauchy's formula is. Now what I'm going to do is, let me apply modulus on both sides. Apply modulus on both sides. So what can I write is modulus of fn of a is equal to modulus of n factorial by 2 pi I into integral over closed curve f of z divided by z minus a power of n plus 1 into dz. As I already told you, if you want to split the modulus, equal sign will become less than or equal to. So let me write this n factorial by 2 pi I. I am going to split the modulus for numerator and denominator as well. So denominator will be modulus of z minus a power of n plus 1 into modulus of dz. Fine. Now again I am telling you once again, remember all these steps will not be given in the notes, so I am explaining in detail just for your reference. Fine. Now in the statement what is given, magnitude of f of z, that is modulus of f of z, will be less than or equal to m. So for the numerator I can replace as n factorial by 2 pi I into integral over c. So numerator will become capital M. Why? Because it is given that modulus of f of z is less than or equal to m. So let me write one more step. Denominator I'll keep as it is into modulus of dz. I'm telling you once again, these steps whatever I'm going to do, I'm just explaining in detail, but it is not given in the notes. If you guys want, you can copy this. Magnitude of z minus a is equal to r. Now I can write this as, when you're going to remove modulus, as per the standard form, I have to write r into e power of I theta, equation of circle, right? Now z will be equal to a plus r into e power of I theta. If you want derivative, dz will be, a is constant, so 0. It will be r into e power of I theta, differentiation is I into e power of I theta into d theta. So again, if you're going to consider magnitude of dz, you will get r into d theta. Fine. Why? Because magnitude of e power of I theta is what? E power of I theta magnitude will be, e power of I theta, how can I write it as cos theta plus I into sin theta. Further, when you're going to calculate magnitude, cos square theta plus sin square theta you will get, right? So cos square theta plus sin square theta will be 1. So as per that I can write dz will be equal to r into d theta. Clear? Either you can do like this, or if you want you can simplify I into e power of I theta. Anyhow magnitude of I will be 1. So if you are going to consider I into e power of I theta, you will get I into cos theta plus I into sin theta. So I into cos theta is I cos theta plus I into I is I square. I square value is minus 1 into sin theta. Again, when you're going to simplify magnitude, so I'll take magnitude here. Magnitude of I into e power of I theta will be sin square theta, that x value is minus sin square theta, right? So minus sin theta whole square plus cos theta whole square. Again, you will get 1 only. Fine. So dz will be r into d theta. Fine. Now I'm going to substitute here. So what is the value I have? Fn of a magnitude will be less than or equal to n factorial by 2 pi I integral over c m as it is. Now what I'm going to do is, what is the value of z minus a? Z minus a is the circle equation. See here, I have written here. Z minus a can be written as r into e power of I theta. When you're going to take magnitude of z minus a, I'll just write here, magnitude of z minus a will be magnitude of r into e power of I theta. As I already told you, e power of I theta value is 1. Magnitude e power of I theta is 1. So you'll get z minus a as r. So I can write denominator as r power of n plus 1. Similarly, mod of dz can be written as capital R into d theta. Right? Now r power of n plus 1, when r comes to denominator, you will get minus 1 here, plus 1, minus 1 get cancelled. So what you left with here is, I'll just write here n factorial by 2 pi I. M I'll take outside, it is constant. Again, see r I am going to shift here only, so that or else I can write r power of n plus 1 as r power of n into r power of 1. So r power of 1 r cancel. So let me take r power of n as constant, it is outside. So you will get d theta here. Fine. So further, when you simplify, what you're going to get is, just write here, magnitude of fn of a is less than or equal to n factorial divided by 2 pi I into m by r power of n. Now integration of d theta is theta, since it varies from 0 to 2 pi. Right? Why? Because it is a circle. It is given equation is circle equation. It varies from 0 to 2 pi. So I can write this as 0 to 2 pi. Now let me simplify n factorial by 2 pi I into m by r power of n. Upper limit is 2 pi minus lower limit is 0. Right? Now 2 pi minus 0 is 2 pi. Anyhow 2 pi get cancelled. So what you're going to get is n factorial by r power of n. So we are left with I, no? So or else I can write this as, see here, dz is r into I into e power of I theta, right? So when you take magnitude of dz, you will get magnitude of e power of I theta. Magnitude of e power of I theta is 1. So let me take that only. So you will get I as it is. So let me replace magnitude of dz with I, you will left here. So I'll just carry I here. Fine. Now in this step I'm going to cancel I and I. I'm repeating once again. When you're going to take magnitude of dz, magnitude of e power of I theta will become 1. So I will be as it is, r will be as it is, and d theta is as it is. Why? Because in the proof I don't have n, so I have to eliminate n. So that is the reason I'm going to carry I as it is. Fine. So I r d theta. So when you substitute dz value, you will get I r into d theta. I'll just write I here, so that I'll carry as it is. Now I have taken outside. In this step I am going to cancel I and I. So what you left with is n factorial into m divided by r power of n. So f power of n magnitude of a. So while deriving the derivation, you have to concentrate at given value. So what we have, n factorial by r power of n into m. So I can write it in a standard format, is less than or equal to n factorial by r power of n into m. So this is what we need to prove is. Suppose if you are going to take I into e power of theta is 1, again you will be getting I in the denominator, but which is not required in the denominator of a given theorem. So that is why I am going to consider magnitude only for e power of I theta. So I am going to retain I as it is. Then I and I get cancelled. So this will be the required proof. Please you just go through this. Further, if you have any doubt, you can free to ask me. Hope so it is clear. Right? So proof is quite simple. Only thing is you have to remember the generalized Cauchy's integral formula. Fine. Now let me explain one more theorem. So there we are using this concept, that is Cauchy's inequality, to prove that theorem. So here is a theorem, and theorem is also called as Liveless theorem. Fine, and it is important. It is asked in the year 2017. Anyhow, I'll send you the notes, but you have to listen the concept. Statement: if f of z is analytical and bounded in the entire complex plane, then we have to prove that f of z is constant. So we have to prove f of z is constant. Now let me prove. So by Cauchy's inequality, just now I have proved, right? So what is the Cauchy's inequality says? So this is what the Cauchy's inequality is. Just now I have proved. So let me write the Cauchy's inequality now. By Cauchy's inequality, what we have, magnitude of f power of n of a will be less than or equal to n factorial by r power of n into m. See, this proof is very short and simple, but when they ask you to solve for 5 marks, you have to elaborate the steps. Like you have to write the whole statement of Cauchy's inequality and try to elaborate the steps, right? So n factorial by r power of n into m. Now what I'm going to do is, let me put n value as 1. So when you put n value as 1, what I'm going to get is f dash of a will be less than or equal to n value is 1 factorial is 1, r power of 1 is 1. That is r. Right, and you can note that as r value tending to infinity, 1 by r value tend to 0. R is equal to infinity, 1 by infinity is 0, right? So meaning is that when r tend to infinity, this value goes to 0. That is, I can write f dash of a is equal to 0. So if you remove magnitude also, I can write f dash of a will be 0. And since a is arbitrary number, I can choose any number. So I can write f dash of z is equal to 0 for any z belongs to arbitrary number. Fine. Now if f dash of z is equal to 0, let me integrate. So when you integrate, what you're going to get, f of z is equal to constant, right? So differentiation and integration are reverse forces. I have a differentiation here. Let me integrate. So you will get f dash of z integration is f of z. 0 integration is constant. So f of z is equal to constant, and that is what we have to prove is f of z is constant. Clear? Now let me solve one more theorem. So here is the theorem. It is called as fundamental theorem of algebra, and this theorem is also important, which was asked in the year 2018. Statement: every polynomial equation of degree n greater than or equal to 1 with real or complex coefficient has at least one root. So whatever may be the degree of a polynomial, or we can write both the statements. So here is a polynomial standard form where a naught and n are complex functions. Usual polynomial is their real number. Here in this concept it is complex function. Then there are n roots of the equation, that is any polynomial which is of degree n. So this is a polynomial of degree n has n roots. For example, if you have a polynomial of degree 2, it should have 2 roots. If you have a polynomial of degree 3, it should have 3 roots. So similarly, if you have a polynomial with degree n, you have to prove it has n roots. So let me prove. So let us consider a given polynomial. So what is the polynomial? P of z is equal to a naught z power of n plus a1 z power of n minus 1 plus so on plus an, and remember a naught should not be equal to 0. Why? Because degree will be changing when n is equal to 0. Now I am going to prove the theorem by using the method of contradiction. Now what we have to prove is every polynomial of degree n should have n roots. Now what I am going to do is I am going to take contradiction. Let me take, suppose p of z has no roots. Roots are same as zeros. Roots are zeros. One more name for roots is zeros, as you already know that. So suppose p of z has no roots or zero. So let me assume that if that was the case, p of z should not be equal to 0 and p of z should be analytical, right? P of z is analytical. Now if p of z is not equal to 0, clearly 1 divided by p of z is also not equal to 0, and if p of z is analytical, I can write 1 of p of z is also analytical, right? If any function is analytical, its reciprocal is also analytical. If any function is not equal to 0, its reciprocal will not be equal to 0. Right? And moreover, as z tending to infinity, what p of z meaning is whatever the function you have in terms of z. So if you apply z tending to infinity, this value goes to 0, right? So I'll give you simple example. 1 by p of z meaning is here you will have terms which contain only z. P of z, that is function of z. If you put z is equal to infinity, you will get 1 by infinity. The value will be 0. So that is the meaning. If z tending to infinity, 1 by p of z will be tending to 0. Meaning is that 1 by p of z is bounded. Bounded in the sense it has particular value, particular limit. Right? So 1 by p of z is bounded. Now as per the Leibniz theorem, what we have proved, if p of z is bounded, what is the Leibniz theorem statement says? That's now I proved. See here, if f of z is any function, f is not only the case, whatever may be the function, analytic and bounded in an entire complex plane, then we have to prove that f of z is constant. Meaning is, what is the Leibniz theorem says? If a function is analytical and bounded, then the function is constant. Now here whatever the assumed polynomial is analytical and moreover it is bounded. So by Leibniz theorem, I can say 1 by p of z is constant. right? But you can note that if 1 by p of z is constant, p of z is also constant, right? P of z is constant. If any function is constant, then its reciprocal is constant. And reverse is here. If reciprocal is constant, we say function is also constant. But clearly it is a contradiction, right? Why? Because p of z is not a constant. Instead it is a polynomial. What we have assumed is p of z is a polynomial. But what we have arrived is p of z is a constant. Which is contradiction to our assumption that what we assumed that p of z has no zeros. If p of z has no zeros, what we derived is p of z is constant. But p of z is polynomial. So it is not possible. Therefore, p of z should has zeros. Clear? I am repeating once again. I have taken p of z as a polynomial. And I have taken that, assumed that by contradiction method it has no roots. So if it has no roots, what we have arrived is p of z is constant. But it is not the case. It cannot be possible. Therefore, our assumption is wrong. Therefore, p of z should has zeros. If it has zeros, one part is finished. That what we have proved is f of z has, p of z has zeros. But we have to prove it has exactly n zeros. So let me prove that. Let me take, since I have taken p of z as, we have proved p of z as zeros. Let me take the 0 as alpha. Say some alpha. Fine. Implies if alpha is a 0, I can write p of alpha is equal to 0, right? For example, if I have a function like x square plus 1 is equal to 0, if minus 1 is the root of this function, suppose I have an equation x square minus 1 is equal to 0. If minus 1 is a root or 0 of this function, then when you are going to substitute here in the place of x minus 1 square minus 1 will be equal to 0. That is, suppose if f of x is equal to x square minus 1 and minus 1 is a 0, meaning is f of minus 1 should be equal to 0. So if alpha is a 0, I can write p of alpha should be equal to 0, right? So I can write z minus alpha 1 of the factor is a factor. In the sense it has one factor. So here in this particular example, x plus 1 is a factor. If minus 1 is a 0, x plus 1 is a factor. Similarly, if alpha 1 is a 0, z minus alpha 1 will be a factor, right? So therefore, where p1 of z is a complex polynomial of degree n minus 1, and it is obvious. Suppose p1 of z has 0, say alpha 2. This is for alpha 1. Suppose it has alpha 2 as a 0, how can we express as z minus alpha 1 into products, right? Z minus alpha 2 into p2 of z and so on. Suppose if we are going to consider one more alpha, how can I write? Like a naught z minus alpha 1, p of z will be equal to z minus alpha 2. It is one of the constant. So we are going to write this as z minus alpha n factor. So it has how many factors? N number of factors. Factors is none other than, suppose if it has 2 factors, we have 2 zeros. If it has 3 factors, we have 3 zeros. Similarly, if it has n factors, we can say it has n number of zeros. That is, p of z has n number of zeros. So that is what we need to prove is. That is the fundamental theorem of algebra. If any polynomial of degree n has n number of zeros. That is what the proof is. I have considered a polynomial and I have arrived that it has n number of zeros. Hope so it is clear. So in the next session I will be doing a very important theorem. Continue in the next session. Thank you.